integer n, and we have to return the least number of perfect squares numbers that sum up to n, which means n, we have to divide that n to certain numbers and add them up, and then the squares of those numbers, it should sum up to n, and those numbers should be minimum. Let's see, for example, from the example, the number 12. By default, I can divide the number 12 into 1 square plus 1 square plus 1 square to so on and so forth, for sure. It's very easy. But this will be 12 numbers. 1 square is one number, 1 square is another number, and that's like entirely, it will keep on going. So I have 12 numbers which sum up to my number 12. Now other can be Rn. I can do, okay, 12 number, okay, 1 square plus 2 square, and then 2 square, and then 1 square, and then it's like something like that. Okay, 4, 8, 9, 10, 11, and 12. So here I divided my number 12 to 1, 2, 3, 4, 5, 6. 6 numbers, and adding those 6 numbers gave me a number 12. But the problem says give me the least number of perfect square numbers that sum up to n. Here my perfect square numbers which sum up to n are 6. The least number of numbers which sum up to my perfect, like to my number, actually n, like n number, is 2 square plus 2 square plus 2 square, which is 4 plus 4 plus 4, which is actually number 12. So 3 is the least number of perfect square numbers which sum up to my number n. As you can see, answer is my 3, which is 4 plus 4 plus 4. 4 is a 2 square. 4 is a perfect square number. And the same way for 13, I can represent that as 4 plus 9, which is the least number of perfect square numbers which sum up to my number n. Now, for sure, you don't know what is the least number of numbers, so you will just go and by default try for all the possibilities. Okay, as in the beginning, I can, okay, if the number is 12, then for sure I can start this number as in, like, I just want the sum, so I can start it with 1 square, I can start with the 2 square, I can start with the 3 square, I can start with 4 square. No, 4 square. Why not 4 square? Because 4 square is 16, which is for sure more than 12 itself. So you cannot add up something in a number and can decrease it. That's not possible. It is not that Sadhu video. If you have not seen it, for the folks who have seen that Sadhu video who asked to add something in something and then reduce the number, so yeah, just comment down below. But for sure, we will have only these numbers to start off from. Now if I have again 1 square, so I will just try to add again. If I have added 1 square, so remaining number now becomes 11. Because now I have to make the remaining number, which is 11, as a sum of squares. If I add a 2 square in the very beginning, then the remaining number will become 8, for which I have to make squares. And same for 9, the remaining number will become a 3. So this only, I will try for all the possibilities of putting a square. So if I have a number 12 in the very beginning, I have a number 12, okay, my remaining is 12, which means I have to now, as a number, as my n as 12, I have to represent that as sum of squares. So I will try on for the initial squares. Now for the initial squares, I have only 1 square, 2 square, or 3 square. That's it. Okay, then if I just add a 1 square, the remaining number from 12 will become 11. Okay, if I have a 2 square as added, then the remaining number will become 8, and then same goes for 3 square, the remaining number will become a 3. Now same go. Okay, again keep on going. If I have remaining as 11, then again you have to represent that as a sum of squares. So okay, try for 1 square, 2 square, 3 square. If I try for 1 square, remaining will become a 10. If I try for a 2 square, my remaining will become a 7. 11 minus 4 is 7. If I try for 3 square, then my remaining will become a 2. 11 minus 9 is 2. And the same way, okay, for 8, try for 1 square, 2 square, 3 square. 3 square you cannot try because 3 square is 9, which is more than 8. Then you will try for 1 square and 2 square. If you try for 1 square, the remaining number will become a 7. If you try for 2 square, the remaining number will become a 4. And the same way for 3 square also, you can try for 1 square, 2 square, but 2 square is 4, which is more than the remaining number, so you cannot try for that. Now you can for sure see up till so far we are kind of applying a recursion tree. We are making a recursion tree, which means we are trying for all the possibilities. It's a brute force approach. But while making this brute force approach itself, while building a recursion tree diagram itself, we saw the remaining number is 7 here, the remaining number is 7 here, which means we will have the recursion, but we also saw that we will have some repeating sub problems also. So for sure we will it will be very helpful if we can memorize that. So while building the recursion tree itself, we saw again, we have not went on completely deep, but in the meanwhile itself, we have figured out that we will have to apply a DP itself while we are actually trying for all the possibilities. Now that is done, that is okay, but let's extend our recursion tree to actually find the answer for the number 12. Right, for the number 12. So we were at this stage, remaining was 4. So again, I'll try for 1 square, 2 square, then 1 square, okay, remaining will become 3. 4 square, like 2 square, remaining will become 0. Oh, remaining became 0, which means I can add a 4, and a 4 to get my final answer as 12. Which means, because see, as you subtracted a 4, remaining became 8, subtracted 4 again, remaining become 4, subtracted 4 again, remaining becomes 0. So as soon as your number becomes 0, you are good to say, bro, great, well done bro, you have got the answer. So as you can see, as soon as the number becomes 0, he can return, okay, that I can just say, okay, this is one step, this is one step, and this is one step. So as soon as the number becomes 0, he can return a 0 itself. Say, okay, I have 3 steps. In 3 steps, I can find my answer. Now, you might have understood that, okay, it's a recursion, which means you are trying for all the possibilities, and it's also a DP, which means you will also memorize that. And at every stage, I will have to try for all the squares, possible squares, which means that I'll try for I into I should be less than equal to n, which means I'll try for all the numbers whose square root is this value should be less than equal to root n. Why? Because I will do a square and then try for that square to subtract in my original number n. This is what I will be trying. So this is a condition which I will be applying. But you might have a slight thought, Aryan, why didn't you apply a greedy? As in, why can't I take the maximum number? Because I want the minimum number of squares. So take the maximum number. It's in front of your eyes itself that if you would have applied greedy, which means the number was 12, you would have just subtracted the maximum square from it, which is 9. Then you would have remaining as 3. But if remaining is 3, then you will be trying for only 1 square, 1 square, and 1 square. Thus, your number of steps would have been 1, 2, 3, and 4, which is more. Thus, you can see by the recursion diagram itself that greedy will not work. So now we have figured out that we will just simply have a recursion diagram. Let's firstly see how the recursion will actually work. As simple as that. With a simple, we will try on for, again, the maximum answer can be n for a number which was 12. By default, I can represent that as 1 square plus 1 square plus 1 square just 12 times. 12 times. So for sure, maximum answer, worst to worst case, can be n, which means I can represent a number n as 1 square n times. That's it. Okay. By default, the maximum answer is n. Now I have to just minimize this answer. Cool. So I asked you, I'll try for all the possibilities, which means 1, 2 square, 3 square, and so on and so forth. Now, up till what point I should try? I square, right? And this I square should be less than equal to my n, right? So I'll say my I into I should be less than equal to my n. This is what I will try. So I'll just say I from 1 up till I into I should be less than equal to n, and I plus plus. Now the square value will be I square. The square value will be I square. Now this I square you will go and try. Just put this I square. Now if you are using one step, which means you are putting one number, so please simply add a 1, which means you have used one number, which is this specific square. Now if you have used this square, if you remembered that if you have used a 2 square, then the remaining number is 8. You will have to try for this 8 now. So one step you have taken, remaining number is now 8. 8 is nothing but in the original value, which was n, minus this I square value which you tried. So n minus square value which you tried. Just simply go and ask the recursion itself, bro, what is the answer for that? And again, you have used one square value, which is this specific value. So please add a 1 for that. And again, I have to minimize my answer. So simply minimize the answer whatsoever is possible, and ultimately return the answer. And for sure, the base case, if you have reached the n is less than equal to 0, or again n is 0 also a valid case, because n will not go less than 0, so n equal to 0 is also good for you. So if it is reached a 0, simply return a 0. As you saw, reach a 0, simply return 0, because at every step I am adding a 1. Okay, 1 here, 1 here, and 1 here. That's it. Thus you can simply see that this will actually would not work, because it's a simple recursion. Why, Aryan? Why it will not work? Because the time complexity for this will be, as you can see, at every level, I will have root n number of possible options, right? Root n number, okay, 1 square, 2 square, 3 square, up till I square, and I square should be less than equal to your n. So I should be less than equal to your root n. So at one stage, I value can go to up till root n. So which means at one level you have root n options. And how many such levels you can have? In the worst case, as you can see, 12, 11, 10. So 1, 1, 1, 1, 1, 1. In worst case again. In worst case. Although I'm saying in worst case because the right part of the tree will be very short. Left part will be very big. So okay, it's kind of in the worst case you can see it is n. N times the depth can go, which means levels can go. So it's kind of root n raised to power h, which means h is the level or the depth you can say. And for sure, for this depth itself, in the worst case, although in the worst case, it will go to n. So it's kind of root n raised to power n, which is okay. Again, it's a very worst case complexity. It will be much less than that, but still, it will give you a TLE. So optimization, we will simply memorize because we saw that it can actually memorize. So we will simply add a few things, just a simple DP line of code while returning, just simply memorize that. Again, remaining code remains exactly same, right? I just initialize my DP with the value of -1, right? N plus 1, why n plus 1? Because I will be accessing DP of n here, right? So I need to have n plus 1 as the initial size, and then simply this is for memorization. And now when this is done, simply one thing that this portion will iterate over root n time. It's up for one level, and you also know that you have your n here, and in worst case n will reach to 0. So if we just imagine, okay, it is sequentially decreasing, so it will reach to 0 in n steps, although it is going much faster than that, but still in worst case I'm imagining it will go decrease sequentially for n equal to 1 for it, let's say. So O of n for here, O of root n for here, so time complexity is O of n into root n, and space is also O of n because of DP which you have built right here. So this is your optimization, and this is what you can find in all the other videos on YouTube. Now let's come on and go a bit more step, although bottom up is not required, it's just for your knowledge. I'm just simply, this is the top down code, this is the bottom code. I just simply use the top down to convert to bottom up. How? As you can see, I know that I will have to go on to all the n. As I go on to all of my n's, I will have to try for all the possibilities of my square root values, which means perfect squares, and then my by default answer can be that number itself. If I am trying for a number, let's say 10, so I know by default the maximum number of square sums which the number can have is 10. 1 square 10 times, and then I will I will try for a square value which is I into I, and then I will just try to minimize my answer. The same way I'll do here, right here. As you can see right here, exactly mapping is on the right side, that I'll try for all the possible values of n. Again, as I try for all the possible values of n, I will just say maximum value for any ith value, maximum number, like maximum answer for any ith value is I itself. Now I will just go and try for all the possible perfect squares, same as this, all the possible perfect squares. Then I'll just simply square that number, and then if I've squared it, I'll simply minimize my current answer by saying, okay, 1, I have taken this specific square, remaining value is I, which is the original value, which is this, minus the square value which I have taken, minus square value, exactly same. It was the original value minus the square value which I have taken, and thus I can simply get my answer in the end, which is DP of n itself. Exactly same mapping done, thus the same complexity and time and space. But now you might have asked, Aryan, you usually discuss DP when you know that you can actually optimize it, and you have asked us that, okay, whenever you have to do optimization in the code, or whenever the interviewer asks you to optimize in the code, then you will have to convert your top-down DP approach to a bottom-up DP approach. But here I can easily see that in usually DP approaches, I can either optimize my space, and the best case I can optimize my time. But for sure, I will have to iterate on all of my possible nums, and for all of them I will have to try for all the square root values of them also, which means all the perfect squares also. And so time cannot be optimized with this DP approach, but space maybe I can, but I can see that, okay, it is not restrictive to just the previous value. Usually in DP, bottom up DP, you optimize that when you can see, okay, your DP of I is dependent only on DP of I minus 1. But I can see my DP is dependent upon the previous much more values. So I need to have all the previous values. So for sure I cannot optimize the space also. So you cannot optimize this bottom up DP approach. Now the interviewer asks you, can you please optimize it? So for sure you won't not be able to think after this if you have not seen this specific video. So now we will study about Lagrange 4 square theorem and Legendre's 3 square theorem, which will actually optimize, and it is the most optimal solution for this approach. Again, if you have not known this, it is no possible chance, again, no possible chance you can solve this problem by this approach, because it is nothing you can drive. You should be knowing these theorems for sure. There is no derivation for this. You are not the professor who can drive this. So let's come and see what this theorem says. Lagrange 4 square theorem just says very simple thing, very simple, very generic thing. It says that any integer, and it is also called as Bachet's conjecture. I don't know why, but yeah, it just simply says that every natural number can be represented as the sum of 4 integer squares. Again, every natural numbers can be represented as the sum of 4 integer squares, which means every number p can be represented as a0 square, a1 square, a2 square, a3 square at max. Again, exactly 4 integer squares. Again, I'm saying sum of 4 integer squares, exactly 4 integer squares. Remember this, I'm saying exactly, and I'm not saying max, I'm not saying min, I'm saying exactly 4 integer squares, which means if I say ask you 3, so it will say 1 square plus 1 square plus 1 square plus 0 square. That's the reason I said add exactly 4 integer squares. So if I ask you, I can just interpret Lagrange's 4 square theorem. Again, I'm saying I can interpret Lagrange's 4 square theorem by saying that every integer or every natural number can be represented as at max sum of 4 square numbers. As you can see, my 31 number, 5 square plus 2 square plus 1 square plus 1 square. So this validates Lagrange theorem. But for us, in our case, 0 square is not being counted. 0 square is nothing. I cannot add a 0 square. It's for me, answer of 3 is 3, not 4. So I can interpret my Lagrange's 4 square theorem saying that, okay, the answer can be at max 4 for any integer possible, for any natural number. For us also it's a natural number. I can have 4 square as sums. So I can easily say that my answer for n, it can be either 1 or 2 or 3 or 4 or 4. But now there's a dilemma. Answer is either a 1 or a 2 or a 3 or a 4. That's a question, right, for you. Okay, you know the answer can be 1, 2, 3 or 4. That's it. But what is the answer? 1, 2, 3 or 4? That's a question. So, okay, that's very obvious. That answer will be 1 if the number n is a perfect square itself. Which means if my number n is 36, so it's a 6 square. Okay, you can simply represent your number as just one square number. So answer is 1 in that case, when the number is itself a perfect square. Okay, great. So this is sorted. We can get to know when the answer is 1. That is sorted. When the answer is 2, which means the number n can be represented as sum of 2 square numbers. Let's name it as I and a j. So you have to find out. So very natural thing which we can do is, okay, I need to find 2 pairs of integers whose square should add up to my n. So I'll try it out. Because it's just a 2 square numbers, right? I can say I can try for all the possible I values, and I will simply square that I value. I'll get a I square. Then I'll do a n minus I square for sure to just figure out what should be the j corresponding value. With this equation, my j square will become n minus I square. Then I will just be searching that, okay, j will become root of n minus I square, and this j should be a perfect square, which means my j square value should be a perfect square. So j into j should actually turn out to be, again, this j, I'm saying this j should turn out to be n minus I square. If this turn out to be this n minus I square, so for sure, my j is a perfect square. See, I'm just simply saying how you figure out something is a perfect square or not. If I ask you, that's a root, let's say if you have to figure out something, root of this number, let's say j, and the value is 25 minus 1, 24 root, which is j. Now you will have to figure out if you do some j into j. Let's say take it as 36. Okay, 6 square 36. So I will have a number which is bigger number 37 minus, let's say, 1. So this, and this is a square. So this is equal, which is 6 square. 6 square is a 36. So 6, which is root, so 6. Now if I just go back and tell that this is a 38 right now, now this will become a 37 right now. So if I just do a root of 37, still it will come out to be as a 6. Now 6 into 6, which is equal to 36, it is not equal to a 37. So number, which means this value which came out, it is not a perfect square. So it is how we can actually figure out if something is a perfect square or not. And I wanted my number, both the numbers, I square and j square, to be a perfect square. So that is how I can figure out that I and j are valid or not. I will simply try for all the possible i's. I simply square that up. I will get a j value by doing a square root, and for sure j into j should be matching my n into I square. If it is matching, so my j square was also a perfect square. If not, that was not a perfect square. So with this also I can figure out if I have two numbers who sum up to my number n. Two numbers square who sum up to my number n. But again, the question remained, how will you figure out for 3 and 4? For 3, again, you will have to try for recursion kind of a tree. Then comes our savior, Adrien Marie Legendre. And he completes the 4 square theorem. What Lagrange gave, he completed that specific theorem and said, I will give you a 3 square theorem. What 3 square theorem says that, again, Lagrange's theorem was very generic, that any positive integer, which means any natural number, you can represent that as a sum of 4 square integer, right? Sum of 4 square integers. He says that I will add up a 3 square theorem and will say that any positive integer n can be represented, expressed as a sum of 3 squares if and only if n, which means your number n, is not equal to of this form 4 raised to power k multiplied by 8 into m plus 7. If it is not of this form, then I can represent any number as 3 square sums. So again, it also says as 3 square sums. He can also add a 0 square. So make sure that part also. He can also add a 0 square. So which means for him also something n number can be represented as this square plus 0 square. That is what he is saying. But still, he can help us know that if the number is not of this form, then it is for sure a 3 square. So I can kind of say that if the number is of this form, which means if my n is equals to 4 raised to power k 8m plus 7, then for sure the answer is actually a 4 squares. So I will have 4 squares as answer. So if my n is of this form, answer is for sure a 4. If n is of this form, again, I'll tell you how to find out if it is of this form or not. It is very easy. If it is of this form, then the answer is for sure a 4. And before giving the answer as 3, make sure he just mentioned, okay, if it is not equal to of this form, then the answer is 1, 2 or 3. But you will have to go and verify first. Okay, first condition is that you will verify if answer is of this form, then the answer is 4. Next condition is if the answer is a perfect square, so the answer is a 1. Next condition is that if we have 2 integer pairs, so the answer is a 2. And last, if none of these follows, the answer is a 3. And that's your answer. So you saw, this is a one-liner thing. This is a O of root n thing, because you will try for all the possible values of I, which is going up to, okay, same, root n. This is again a O of 1 thing, and else condition, which is the super n thing. So now, coming on back, that firstly we have to go and find out this, if it is of this form or not. Simply, I know that this is a form 4 raised to power k 8m plus 7. Please just simply remove the parts which you can remove. So I know that this is a part which I can remove. So I'll do, okay, if n mod 4 is equals to 0, is equals to 0, then simply remove this portion. So I'll divide by 4. And I'll simply remove this entire portion. I'll simply remove this entire portion. Now this entire portion is removed. Remaining portion is 8m plus 7. So I'll say if n mod 8 is 7, because you will see 8m plus 7, if you do by mod 8, it will become 8m mod 8 and plus 7 mod 8. This will become a 0, this will become a 7. So if this value is a 7, which means it is of this form. If it is of this form, we know the answer will for sure be a 4. So simply return a 4. Return a 4. Okay, return a 4. And you can also see that, okay, if it's a perfect square already, we return a 1, which means I just simply got the square root value for that number. If the square root value into that value becomes a number n, which means that was a perfect square. So I can give a 1 itself. Okay. Now when this is the case, I can simply say, okay, my 1 case is done, my 4 case is done. Next case is my 2 case. For that, I'll simply iterate on all the possible values of my I up till root n. I'll get the square a value, right? Then I'll just do n minus square a value. I'll get a element b, and that element b into element b again. That's a square root right here. So element b and element b into element b should be equal to my this value whole square, which means this value itself. Square root of this value is nothing but square root of n minus a square, which is this element b. I just want, okay, b square should be equal to n minus a square. That is it. I want it actually for this b square to be a perfect square. So I'll just say if this b into b should be equal to n minus a square, then for sure this b square is a perfect square. So I'll simply go back and say that I can simply return an answer as 2. Again, math thing. For the people who are confused, again, many people will be confused on what is in this b square and stuff. For that, I have explained this specific diagram for 6 square. So please keep a pen and copy with you, and without that, please don't just say that, okay, this is not understood. Have a pen and copy and try them for some other example also with you itself if you want to actually add on. Right now, this is a 2 square. We can actually have an answer as 2 returned. So okay, our answer of 2 is also done. In the last case we saw, else I will simply return a 3. So with this, you can see that you just tried only of root n. Because of this, to find the sum of 2 perfect squares, that was a root of n time, and space is O of 1. That's the most optimum approach. Now, last but not least, I'll discuss a BFS approach. Although this is not the most optimum approach, but this is an approach which you can only know after knowing this math approach. How? If you go and look back at the recursion tree diagram which we made while discussing the recursion and top-down DP, we made the diagram something like this, which was going on because, you know, at every level I will try for root n values. So if you remembered, I was trying for root n values. Now my Lagrange's 4 square theorem and Legender's 3 square theorem, these adding up says that I will for sure have maximum of 4 square. Again, Lagrange's 4 square theorem is more than sufficient for you to say that at max I will have 4 squares which can add up to your answer. Right. So rather than applying a DFS function which will go up to the super depth of the answer and then come back, rather than applying that DFS function, we will simply apply a BFS function. Okay, BFS on the first level, second level, third level, fourth level, and I for sure know by Lagrange's 4 square theorem that at the fourth level I will for sure find the answer. So my level will never go beyond 4, and that is the reason I should apply a BFS which go breadth wise, which means level wise. That's the reason for this approach. Better approach is to go and start off with a BFS rather than DFS. And here comes the fact that you should be knowing what's the difference between a BFS and DFS and when can be applied. So because we know that we can obtain an answer at an earlier level, so we should not go at the very depth of any other branch of the tree. So I will just go level wise because I know at the fourth level I will for sure get the answer. That's the reason. If we go back and look at the complexity, that was root n raised to power h, because root n for every level and h was the depth of this entire recursion tree. But now I'm saying I'll restrict that depth to a 4 because I know the depth can never go, because I'm going level wise. So I will for sure never go beyond the depth of 4 or the level of 4. So answer will be root n raised to power 4, which is O of n square. Although it is even more than O of n root n, which was because of DP, but still this approach you should be knowing to just understand the difference between BFS and DFS and how that is actually useful. And again, you could have only understood this by only knowing the fact that we have Lagrange's 4 square theorem kind of theorem, right? And that's how you can simply solve it. So in this video you saw recursion, brute force, top down, bottom up, math, Lagrange's 4-square theorem, Legendre's 3-square theorem, and BFS approach, and the difference of BFS and DFS. Cool, thanks for watching. See you, goodbye, take care, bye bye.